Hello everyone. Now we are getting to the final stages of this course on digital system design, and we are going to look at a few slightly, well, not exactly advanced topics, but things that you would use in order to optimize your designs, and then also certain aspects of what goes beyond what we have considered so far. So we are going to start by looking at the problem of performance optimization. So far we have looked at various different aspects of the basics of digital design, right, where essentially the way that we went about digital design was we started off with a review of combinational logic, sequential logic, then got into the details a little bit of how we can do hierarchical design, basically looking at modules, right. Use modules to build up larger components, right. Those components can in turn be assembled into subsystems, eventually leading to systems, right. And we sort of, the last stages of the discussion were how we can have a system on chip. So in all of that we talked about the basics of synthesis, how synthesis works and so on, but not really about how we would optimize for, let's say, speed or area or some other parameter, right. So let's look at that in a little bit more detail now. So I'm going to use this example, a very trivial kind of circuit, in order to try and illustrate one aspect of how we might be able to improve the performance of a circuit, right. So what exactly does this represent over here? Essentially what I have in mind is something where these gray boxes, right, the gray rectangles that you see over here are registers, and the green circles essentially correspond to some kind of combinational logic, right. So as you know, essentially this is a path through the circuit, right. And of course what I have drawn over here is a highly simplified model which basically sort of gives you the impression that there is a single signal sort of passing through over here, some computation happening with it, that in turn gets forwarded to the next unit, again some computation happens, and so on. Now in practice it's not as simple as this. Each of these blocks, this circle as well as the other circle, is going to correspond to a number of different gates, right. There may be AND gates, OR gates, full adders, NOT gates, and so on, that constitute this, which also means that it's not just one signal that's coming in here, it's a whole set of different values, right. So when I draw a register over here, what I actually mean is sufficient number of flip-flops so that all the signals that are coming in over here are registered, right, are sort of captured at this point, and there is a clock that basically determines when all of those signals come through and are ready for starting the computation, right. That is after all the basic idea of synchronous digital logic, right. You have a clock signal which basically determines when the signals come out of the register, and from there they can pass through combinational logic and must be ready at the next register at least one setup time before the corresponding clock edge appears at this second register. So the diagram that I have drawn is a highly abstracted out and simplified version of what we are trying to do here, okay. Now let's look at what we would actually end up with, right, assuming that the delay through this is some TA and TB, right, and I'm further going to assume that I can ignore the TCQ, right, which would basically be the delay over here, the clock to Q delay. I'm going to assume it's approximately equal to 0, and similarly I have another T setup at this end which I will also assume is approximately equal to 0. Now as we know, there is also a third parameter called the hold time, but the hold time is more important when we are sort of looking at, can the signal that comes out over here race through this and get to this second flip-flop before the hold time has passed on that flip-flop, right. And as long as there is some finite delay TA and TB over here and some logic, that kind of hold violation is not really going to happen. So at least for this circuit and for finding the speed at which it can operate, I am going to ignore the idea of the hold time. And as I said, I am also sort of assuming for now that the TCQ and T setup are negligible. Okay, so with all of that in mind, what can we say about the clock period that can be used on this circuit? We can basically see that the clock must be greater than or equal to TA plus TB, right. This is a requirement. All that it says, it must be greater than or equal to, right. As long as it is not less than TA plus TB, there is sufficient time for a signal coming out of the register passing through A and B, and so that it is stable and not changing anymore before the next clock edge arrives on the second set of registers. Exactly at the same moment when the clock edge arrives on the second set of registers, we also assume that a clock edge is arriving once again on the first register, which means that new data is getting pumped in to the entire circuit, right. So the way that it works is some data sort of goes through this, some computation happens, it gets saved over here, and at the same time something new comes in from this register. So this is literally how we define sort of clockwork or heartbeats or any kind of a very regular event that's happening, right, and that's how all synchronous digital circuits are expected to work. Okay, so we know that the critical path for this circuit is TA plus TB. Now the question is, what can we do about this? Is there any way in which I can reduce this clock period? Because if I want to run a circuit at a higher speed, clearly I would like to have something which allows me to run at a shorter clock period, meaning a higher clock frequency, right. And what we looked at in one of the examples earlier was, for example, let's say that this entire circuit represented something like a parallel multiplier, right. The alternative might have been some kind of a sequential unit, right, a sequential implementation of the logic inside this, where I say that there are some kinds of registers and some logic and feeding back into the same registers. This would constitute some kind of a finite state machine. It would take certain inputs, it would have certain outputs, right. Some of the inputs may either go directly into the flops, outputs may come directly from the flops, but at the end of the day I can replace this entire structure that's internal over here with some kind of a finite state machine plus a data path that actually performs some computation, right. And why would we do something of this sort? The idea is, rather than having a critical path which directly goes through TA plus TB, well, one thing to keep in mind over here is, if I do have this kind of combinational path directly through this, then yes, once again I may end up with a long delay. Typically that's not how data paths and control are designed. So I might want to have it such that the actual longest path that I face over here is less than TA plus TB, right. In fact, ideally if I could have something which could bring it down to, let's say, TA plus TB by 2, I could double my clock frequency because my clock period has become half, right. The problem is, there is a finite state machine, which means that it's probably going to take me 2 clock cycles to actually finish the work, right. So it's not very clear that I could actually save the time in order to generate a given output, right. But it may be possible that my entire circuit could run at a higher speed. So this diagram is a little bit complicated, it's a little bit busy, but I'm going to use this in order to try and explain a few things, right. What we have talked about, this so-called the normal implementation which just has t greater than or equal to TA plus TB, which by the way is more or less what you can consider as the behavior of the single cycle CPU in the discussion of the CPUs that we were using before, would correspond to something like this, right. We have a long clock period, right, and the first set of inputs comes in here, it takes a certain amount of time and it generates an output, right. That output is basically ready to be sampled at the next clock, during which the next set of inputs has come into the system, right. So the next inputs have come in here and B gets computed and is ready by the next clock period. After that, C gets computed, gets ready by the next clock period, D comes in, gets computed, and so on and so forth, right. So as you can see over here, each individual computation A, B, C, D and so on takes a certain amount of time, and the clock period that I use for the system is basically double or well, is basically equal to the total time required to pass through all the combinational logic. Now let me assume that I have somehow managed to create this kind of sequential unit, with this finite state machine based output, where I have 2 stages, right. So I could think of it as a 2-state machine, right. I get the input, I have stage 1, I have stage 2, this produces an output, and I go back into stage 1, okay. The diagram for that would look something like this. notice over here that the clock period is much smaller than before, right? Why is that? Because stage 1 has a critical path which is equal to, let's say, TA. This has whereas stage 2 has a critical path which is equal to TB. And assuming that TA and TB are more or less equal, right, we will discuss that in a moment. TC is equal to TA is equal to TB is equal to basically TA plus TB by 2, right. So what we have over here is this TC that you see over here in this diagram, obviously this is an ideal version of the diagram, is half of what we had earlier, okay. Now let's look at what's happening in there. There is something that I am calling stage 1, right, which is basically performing a computation, and I am calling it the A1 computation. That is to say, it takes the first input and allows it to pass through the A module, or rather the first module over here, right. After that, what I have is I call it the A2 computation, which in this case actually happens out here in the module marked B. Please pardon the slightly confusing terminology, right. What I mean over here is that there are two modules. You can think of it as the first module and the second module. There are two stages, stage 1 and stage 2 of the finite state machine, right. And what happens over here is in the first stage we basically have A1 being computed corresponding to this A, right, but the final computation, or rather the final output, is not yet ready. In the second stage, the output of this A1 is being used in order to compute A2, right, and which means that by the end of the second clock cycle, the actual output, whatever I had computed over here, is also ready at this point, okay. Now what has happened is I took 2 clock cycles in order to perform a computation. Just like in the case of a sequential multiplier, I might have taken maybe 8 clock cycles in order to actually finish a full 8 cross 8 multiplication or something like that, right. In this case I am just keeping it simple and assuming that I have only 2 stages in my finite state machine, and therefore within 2 cycles I have managed to finish the computation. There are a couple of important things to notice here. The first is of course the fact that the TC for my multi-cycle implementation, right, and once again the analogy can be drawn to what we talked about in the case of the CPU, right. The single cycle implementation had a long critical path. The multi-cycle has a shorter critical path because each individual stage in the finite state machine has less logic associated with it, but it takes 2 stages in order to finish the computation, right. So I have a shorter critical path, but I take 2 cycles, so eventually the time ends up being the same, right. Okay, now what happens after A2 has completed? In other words, the output corresponding to A has got generated out here. I am ready to accept the next data, right. My finite state machine goes back to state 1 and I basically accept B and start computing B1. By the time I have finished over here, I then hand it over to B2, and B2 basically takes until the end of the clock cycle, and over here whatever would have been computed by the single cycle system is also computed here, right, in the B2. Similarly, after that I go forward to C1 and then I go forward to C2. So far so good, right. So this is essentially the distinction between the single cycle and the multi-cycle CPU that we talked about, but as you can see I am not really talking about a CPU, I am talking about any general kind of digital logic where I can think of it as a path starting from a set of registers, ending at another set of registers, passing through some combinational logic in the middle, okay. Now of course you have already seen this picture, so you must be wondering what's happening in the third set of waveforms that we see over here, right. If you look at it, it looks as though it's got a TC which seems to be the same as for the second, right, the 2 cycle system, right. But at the same time, if I look at the data that's coming out, it looks as though there is more data being produced, right. So let's try and understand this a little bit more clearly. So let's just go over that discussion of this multi-cycle system once again, right. What I have is I have a piece of logic, not call it A, let me call it stage 1, and there is another stage 2, and finally there is another register at the other side, okay. And what I am saying is that the computation that I expected for A, it first has to go through stage 1, the output of that has to go through stage 2, and this basically comes out as the output, right. So in the normal single cycle scenario, basically it would have just gone through combinationally, right, through stage 1 plus stage 2 to the output, which is why I end up with TA plus TB as the actual total delay, right. The T critical is greater than or equal to TA plus TB. Now instead what I am doing over here is I am replacing this entire logic with something which has a finite state machine plus some logic, right, and I have inputs and I have outputs. This basically takes stage 1 as one state, stage 2 as another state, the computation goes through, and I then go back and repeat the entire performance. So in this diagram, when I mention A1 for example, what I mean is it's the partial computation required for computing this final value A. Whatever has got computed in A1 is then passed on to stage 2, where a further computation happens, and whatever I get as A2 is whatever would have normally come out through the combinational logic directly as A, right. So going through this, in other words, the first input I will consider it as A. I need to essentially pass through both this combinational logic and get to this point. In combinational logic, I just pass through stage 1 and then through stage 2, and the output is ready. In sequential logic, I would explicitly pass through one state, go through the second state, but the final output that I generate over here is still exactly the same as having passed through these two pieces of computation, right. So these are the two different ways by which I can implement this, right. I have a critical path out here, and it can basically be broken up into two phases, right, A1 and A2, but the final result after I have computed A2 should be the same as a direct combinational computation of A. Similarly, I can take B and break it up as B1 and B2. I can take C, it would be broken up as C1 and C2. So my assumption is that this logic that I have over here, I could break it up into two stages or two states and implement a finite state machine that performs the computations one after the other. In order to do that, obviously the output that I generate from A has to get stored into some registers, and then it basically has to get fed back for the next stage computation to be performed, and the final output comes over here and goes into the second set of registers. Okay. Now the so-called pipeline system that I have drawn over here is very similar, except that it looks something like this. I have my logic, I have my stage 1 compute. Now what I do over here is I put in another register, right, and then I bring in my stage 2, and then I finally have my final register. Now what has happened over here is I don't actually have a finite state machine. What I have done instead is I just say that whatever was computed from stage 1, I put it into a set of registers over here. So in some ways I am actually simplifying the logic compared to the finite state machine. But the question that you might ask is, look, is this even okay? Because after all, what I have done is I have just gone and inserted a new set of registers out here. Isn't this in some way changing the final data that comes through to this point, right? The answer is, it is changing it, yes, but it's only changing it by sort of delaying it by one cycle. What we are saying is, if I apply A at some point, some computation will happen and A1 will come here. That A1 will then sit over here and be ready for the computation of A2, right, in the next clock cycle. Now what has happened as a result of adding this new register out here is that the moment that this A1 has jumped across this register, I no longer care what's happening on the input side, right. And what that means is I can actually apply a new input which I will call B1, right, at this point in time. B1 then goes through stage 1 while A1 is going through stage 2, right. So that by the end of the second clock cycle, A2 has been computed exactly the same as what I would have expected before. In the meantime, B1 has got computed and is now sitting ready at the input of this register and will get stored into this register when the clock cycle or when the clock tick happens. Okay. What does the corresponding waveform look like? It looks like this third diagram that I have here. Right? The critical path in this case is once again equal to TA or TB as the case may be, right? And the reason why it is that is because after all I have broken it up into two stages by putting this register in the middle out here, right? So this critical path says TC greater than or equal to TA, this says TC greater than or equal to TB, right, or T1 and T2 as you may want to call it. Now let us look at what computation is actually happening. Stage 1 performs the A1 computation and basically hands it off to stage 2, which then goes ahead and performs the A2 computation and the data is ready here. This is exactly the same as what we saw here, right? The A1 gets computed at this point, the A2 gets computed at this point, and therefore I end up getting exactly the same result as what would have happened in the finite state machine based two cycle system, which we already saw was exactly the same as having a long critical path based pure combinational system. Okay. The big difference between the what I call the non-pipelined and the pipelined approach is that at the second clock cycle I can now feed in a new set of values over here which basically corresponds to B. I don't need to wait until this point. When I had a finite state machine which was telling me, okay, you are either in stage 1 or in stage 2, you cannot be in both at the same time, I could not do that. But by actually simplifying my design over here and just saying, add a register out here, what has happened is I have effectively separated out the two stages into independent components, right? And I am able to say that I can apply the second set of inputs, the B input, directly at this point, because after all, this logic over here, stage 1, is not doing anything when my finite state machine is in stage 2. Okay. Instead of that, I apply a new set of inputs out here. It goes through the first piece of logic, stage 1, and is ready at this point in time. Now, once again, when this clock ticks, right, A2 is now ready. It has got stored into the register and therefore is seen by the outside world. In the meantime, B1 is ready and gets stored into this middle register and is now ready to go into stage 2, where of course it goes through and gets computed as B2. While that happens, I can apply a new input, C1. By the time B2 gets computed, C1 is done and is ready to go through as C2. D1 can be applied as input. So if you look carefully, what you will notice is that even though the time required to compute the first A was still equal to TA plus TB, right, the total time required for the delay, right, or more importantly, it is 2 times the clock period, right. What happens after that is every TC there is a new output. Okay. And this is a crucial difference. This is the difference between a general sort of multi-cycle implementation versus what is called a pipelined system, right. Now, the origin of the idea of a pipeline comes from actually assembly line manufacturing, which was introduced on an industrial scale primarily in the manufacture of cars, right. The idea being that in order to build a car, there are many different steps involved. There is a chassis that needs to be assembled, there are wheels that need to be put in place, there is an engine that needs to be installed, right, and there is a definite sequence of events that happens out there. But on the other hand, the equipment required for the chassis installation versus the engine installation versus the steering wheel or the painting at the end are different, right. It is not that you can reuse the same hardware in order to do all of them. So the thought process over there was, let me first finish building the main chassis, push it off to someone else who will go and install the engine, and in the meantime I can start building the chassis for a second car, right. I don't need to sit idle until the entire car has got completed. That's exactly the same thing that's happening out here. As soon as stage 1 has finished with the A1 computation, it can move on and start doing a B1 computation. It does not need to wait until A2 has also got completed, right. Now, it may look, when we look at this diagram in this way, that this is a very obvious thing to do. After all, why did I not just insert this register over here, right? In fact, why should I stop there? Can't I even further break it down and maybe even make it smaller, right? Can I break this down into further stages and so on? Now, the answer to that is a little bit complicated and is a little bit beyond the scope of what we can cover in detail in this course, right? It requires a little bit more sort of understanding of how dependencies are captured in terms of data flow graphs and so on, right. But at a very high level, it ultimately comes down to a question of trade-offs, right. Plus of course of whether the computation is correct in the first place. Now, the first thing you need to understand over here is that if I have a piece of logic like this, right, where there is, let us say, 2 blocks followed by a register, right, is it even valid for me to insert a register at this point, right. And in order to understand that, you need to realize that after all, inputs are coming in here at a regular rate, right. What is happening is there is some computation which ultimately is supposed to pass through both of these units and finally supposed to come out of this register. By inserting this new register in the middle, we are delaying everything by one cycle, right. Now, in general, there is no problem with that. Where it becomes a problem is if you have so called time variant systems. In other words, for time variant systems, this is not permitted. I cannot just delay something by one cycle and expect that the behavior is going to be the same. In other words, if this individual combinational blocks, the blocks that I have drawn as combinational blocks, had some behavior which in turn actually depends on time, then just randomly inserting a delay element here and saying, okay, I will just take everything one cycle later, actually changes functionality and is not permitted. Now, combinational logic by its very nature is time invariant, right. Adders, multipliers, they do not depend on what time you give the input to them, they will always produce the same output, which means that for most of the regular kinds of digital logic that we are trying to implement, this is actually a perfectly valid thing to do, right. Now, that sounds good, right, but what if I had a circuit that looked something like this, right, where essentially, let us say I had this logic, I had some combinational logic out here, but in addition I also had something which basically went from here and went back to this point, okay. Now, if I say I am going to try and insert a register out here, this has actually changed the functionality completely. This is wrong, I cannot do this, right, because what has happened is there was some computation that was going through and was expected to come back at this point. By adding a register out here, I am actually changing the functionality in a very non-trivial way, right. When you look at something like, when you look at this in the context of a course like signal processing systems, digital signal processing, this will become a lot more obvious, right. Effectively, what we are thinking of is that this is similar to what we think of in terms of an infinite impulse response filter, right. We have a certain computation that is being performed based on x of n minus 1 and so on, right. Over here, what we are doing is effectively changing that and saying I am taking a different value and feeding it back in over here, right. There is no way that I can correct for it, right. If you have not done signal processing, then do not worry about it, it is not relevant to the rest of this course, right. It is just that it might become a bit clearer when you get to that point, but we will not be going further with the sort of analysis at this point in time, okay. So, this is basically where pipelining, as I have shown over here, where we essentially just try to insert a new register or delay element, right, may break down, right. It is not always possible, right? You can't just take any combinational path and stick a register in there and say, okay, I'll reduce the critical path. There are many scenarios where that actually changes functionality and is not permitted, right? But there are scenarios where it is actually permitted and where it makes a lot of sense, because if you are able to successfully do it, what we get over here is the time taken for individual outputs remains the same as before, right? That's called the latency, but the time per output has now become half of what it was in the original case, right? So if I look carefully at this diagram, what I have is something like this. With a pure combinational logic, I would end up with something like this. The clock period would be greater than or equal to T1 plus T2, right? Which basically means that the latency, right, which is the time required to generate one output, is equal to the clock period, and the throughput is basically going to be given by 1 over that clock period, okay. Now instead, if I had a pipeline system, what I have is, I have a system which looks like this, right. So this is T1, this is T2. I am going to assume that T is equal to T1 is equal to T2, right. Assume that for the time being, right, T1 and T2 are both the same, which basically means this is equal to the original T1 plus T2 divided by 2, right, because T1 is equal to T2, which is also equal to T1 plus T2 by 2. So in other words, the clock period that I have now is half of the original clock period that I had for my single cycle system. So I'll call this TP just to be clear, right, and this I will call as single cycle, TS, okay. Now what we can see is TP is equal to TS by 2, right. What about the latency over here? The latency in this case is still equal to TP plus TP, because after all I need to pass through one stage and through the second stage, which is basically equal to TS. So in other words, the latency remains exactly the same as before, but the throughput, right, which is, you can think of it as how many samples are getting processed per unit time, right, that is basically going to be equal to 1 over TP, which is 2 over TS, right. So this is a crucial difference. Effectively what has happened over here is my original throughput was 1 over Ts, because every Ts units of time I can process one sample, whereas over here I am able to process one sample every 1 over Ts by 2, 1 over Tp units of time, or 1 over Tp samples per unit time, okay. So pipelining, in other words, allows us to increase the throughput without really changing the latency, okay. That is the ideal scenario at least, okay. Now hopefully this part of it is clear, right, what is the difference between pipeline versus single cycle. Just for to repeat, you know, that you cannot really get the benefit of this from a multi-cycle implementation, right. If I had, let's say, a multi-cycle implementation, it would look something like this. I would essentially be drawing a finite state machine over here, right. What would end up happening over here is that the clock period would be equal to T1 plus T2 by 2. This I'll call it the multi-cycle clock period, which is the same as the pipelined clock period, right. The latency in this case would be equal to 2 times the multi-cycle clock period, which would be equal to the single cycle clock period. The problem is when I go and look at the throughput, right, I can only get one output every 2 TM clock cycles, which is basically the same as the single cycle throughput, right. So the multi-cycle implementation that we have over here, right, does not improve my throughput, whereas the pipeline system can actually double my throughput by effectively just adding a very simple amount of logic. All that I have done is added a few registers in the middle, okay. Alright, so this is the basic idea behind how pipeline systems work.